Okay, so I will be recording this part of the session. So if anybody has any objections with the recording, please say so now. Okay, so we are going to be now talking about controllers. And so all of the journey we've had up to this point takes us to this topic. So we already saw how we can model a system. So modeling means I'm going to represent it as using some sort of mathematical tool or concept or even a software where I'm representing what's happening in real life into a model that I can manipulate. Once I do that, then I can create and connect different models of systems to create other systems, larger systems, feedback systems, in which I can analyze how these systems behave with regards to their transient response, which means the moment where I input a new signal to the system or a new stimuli to the moment it stabilizes. I can also analyze stability of the system. I know that all of this is in the end related to the transfer function and the poles of the transfer functions and how these poles are located in the complex plane, in the S plane. Also, I know that depending on how the characteristic equation of the system is structured, I can also know the type of the system and how the steady state response is. And depending on how I plot or locate the poles in the S plane, I can represent different configurations of the system depending on different behaviors I want for a particular variation of a parameter. And that's called the root locus. And so all of these takes us to the point where, well, we can incorporate formally what we've been doing informally up to this point, the concept of a controller, which is going to be this subsystem that I can manipulate to manipulate the transfer function of the system, and by doing that, manipulate or change the behavior. And so a controller is also called a compensator, okay? So in control systems theory, you can find the term controller and compensator. They're interchangeable. And basically, the controller is going to receive the error of the system, which is this comparison between the actual value and the value or reference we want. And the purpose of the controller is to do everything possible to reduce the difference between these two, or try to make the error be zero. This is done by generating a control signal that's provided to other parts of the system to modify the behavior. So if we look here at this diagram, this is the general representation of a closed loop system. We have our different elements, the actuator, the plant, the feedback, and we usually have a box here or an element where we can, up to this point, we've identified an element here where we have a certain K that we know that if we manipulate that K, we can manipulate the behavior of the system. Now we're going to look at different configurations of this box, not only a K, that can do the same thing and specifically address certain aspects of the system design. Now, there are different types of control actions. The compensator or controller can have different ways of working. In general, we have these classifications of controllers: the on-off control, the proportional control, the proportional integral, proportional derivative, and the integration of all of them, which is a proportional integral derivative controller, or what's commonly called as PID, or the PID controller. It might be common that many of you have already worked with PID controllers for in an integrated way in your projects, and you've had to deal with calibrating these constants to try to make the system behave differently. So each of these constants, the proportional, integral, and derivative constants or parameters, these do a specific action in the system, and manipulating them can generate specific results that we want in the system. In the end, what we're really going to be talking about is this one, which is a PID controller, which integrates all of the control actions that we need. And these are called control actions, okay? And so let's talk a little bit about these. So now we're going to talk about these controllers and what characteristics they have. So first off, the on-off controller, and I'm just going to mention this controller very briefly, but basically the on-off controller is a controller that only has two values, okay? When the error is above 0, we're going to have one action. When the error is below 0, we're going to have another action. And so think about your air conditioning, okay? You've got a reference temperature. Depending on if it's above or below that reference temperature that you want, so the actual temperature, depending on if it's above or below the reference temperature that you're establishing, the AC is going to turn on or off. Now, this is what's called an on-off controller. So basically the only thing you have is a comparator. So if the error is above a certain value, turn something on. If not, turn it off. Now, if we do that, we're going to have the following effect. Let's say you put your temperature at a certain value, and when it goes above the value, you turn it on, but then the temperature gets lower, and then you turn it off, and then it gets hotter, and then you turn it on again, and there's this effect that's called hysteresis, which is basically this switching on or off when you have this fixed parameter. And so usually what happens is that with an on-off control, you set what are called thresholds. So instead of setting one temperature, you set that temperature or reference value plus a certain value and minus a certain value. And even check your AC controllers. If you have your AC controllers in your house, there is a way to check that threshold. So you can establish that threshold. Notice when your AC turns on, let's say that you have it at, I don't know, 78 degrees. When it gets to be 78 degrees, it turns on, okay? And notice that it turns off at a certain value. You can check that value. For example, I think with our AC here in the house, I think it's 1 degree or 2. So it's going to turn on at 79, and then it's going to stay on, and so things are going to get cold. Okay? It's going to get cold, so it's going to the temperature is going to lower, and so when we go below the 79, it's not going to turn off. It's going to turn off until it reaches 78 or 77, depending on the threshold that we establish. So it's going to turn off, and then it's going to go up again. And when it reaches the certain value, maybe plus or minus the threshold, it's going to also turn on again. And so that threshold is what we established to go around this hysteresis effect. So the on-off control is before the proportional control, it's probably the most simple control that exists. Now we've got the proportional control, which is the one we've been talking about. And so the proportional control is simply that the control action is going to be proportional to the error. So if I have a lot of error, I'm going to multiply that by the control action, and the result is going to be large. If I have a small error, I'm going to multiply by that, and it's going to be small. And so the output or the control action is going to be proportional to the error. And that's why it's called a proportional controller. Up to this point in the examples we've seen, remember that we've always had a K that we're trying to manipulate or define values of K for stability, for certain design parameters. Well, up to this point, that K has been the proportional controller variable that we have that we can manipulate. The transfer function for a proportional control is simply the value of K. It's basically, if you guys are taking analog electronics, while you're taking analog electronics 2 and you're working with amplifiers, well, basically, a proportional control is an adjustable gain amplifier. Okay, so that KP could be a combination of resistors in an operational amplifier setup or a transistor setup, for example. It's going to simply be the proportional action of the being done to the actuator, and this proportional action is going to be proportional to the error of the system. Okay. Questions up to this point before we move on? Okay. Now, the next type of controller action is a combination that's called the proportional integral control. We usually don't talk about the integral and derivative controls by themselves. So we could talk about the integral action or just the derivative action, and these are called lead and lag. But they're usually done in combination. So we're going to have the integral control combined with the proportional. And how is that going to look? Well, mathematically and literally, the proportional integral action is going to be a combination of the proportional action with regards to the error, which is the same one we had in the proportional control. And now we're going to incorporate the integral of the error. Okay. Also with a set of constants, which are going to be these here, which is usually a combination of the proportional divided by what's called the integral time. In the end, all of these constants are combined into 3 constants that we use for the PID control. And so if we were to apply the Laplace transform to all of this, we would find that the Laplace transform of calculated the transfer function, we would find that the Laplace transform of Kp is just going to be Kp, and the Laplace transform of the integral, or I'm sorry, rather, the Laplace transform of there's going to be Kp. The Laplace transform of the integral and the controller actions is going to be Kp divided by Ti, which is the constant that's defined for the integral control, divided by S. So there is the S that we were looking for, that Luis mentioned. By adding the integral, we're automatically going to add an S. If we add these two and factor and do the common denominator, in the end, we get that the transfer function is this one that's here. What do we see here with the integral and that transfer function is that we are adding here on the bottom this S that we were looking for to automatically increment the type of system. So whatever type the system was before, after applying the integral controller, the type automatically increases by 1. And we're going to talk a little bit about this term here on top. So we're also adding another term on top, but if we make this small enough, it's something that isn't going to affect the system. Okay, so this is the kind of the overview of the PID controller and how it's represented mathematically. Now, another representation that's much simpler, actually, and it has the same effect in the end, is the following. I can just grab everything and just use 1K to represent both actions, multiplied by S plus A, which A is going to be a pole, a very small pole that we're, it's going to be a very small number that we're going to add there as a 0, and S, which is the S in the denominator, that's going to increase the type. So the PI controller is basically going to help us improve the steady state performance of the system, or reduce the steady state error. And how is it going to do that? Because it adds this S in the denominator that's automatically going to increase the type. And so basically what happens is the following. Let's assume that we've got a system that has the following root locus. So it's the system in blue. So in the system in blue, it has the root locus that's represented there. So let's say that we're using the root locus and say, you know what, I want an overshoot that's less than a certain percentage. And I find a value here for that. And so the blue line here is the response for this value. And I've got a certain error here. If I could add or be able to select another pole that would be in another location, and I'm going to call this one B, where I'm adding basically adding another pole to the system. This is going to help me have the response, which is in the black graph, which is a response that's a little bit better and reduces the error. So what I'm actually doing also, remember, when I'm adding the controller, is that I'm reconfiguring the root locus to be able to have other alternatives for poles and zeros that comply with the system and therefore can have different behavior. In the end, remember that the changing of the poles of the system or the reconfiguration of the root locus is going to provide me these different behaviors. The same thing here, assuming that we've got just a proportional controller and we've got a value of A, by adding the compensator, the root locus is now going to be completely reconfigured. And that's what the compensator does. And so the new root locus is going to have a new value that's going to provide the better behavior that we're looking for. Now, let's look at this in an example. So let's assume that we have the following two examples here. Let's put them over here in MATLAB. Let me switch over here. So I can switch over for both. You can see my MATLAB here, right? Okay.
Yep.
Okay, good. So I'm going to be switching over between the screen and the button. So let's assume that I'm going to clear all CLC. I'm going to create a system. I'm going to call it sysplant, which is basically the one that we have here as a plant. It's going to be TF. Let me change my keyboard here. TF. And the denominator, we have a 1, then the convolution of 1 of 1 times the convolution of 1 2 with 110. Check all of the parentheses there. And then I'm going to create the compensator that we have here. So we're going to define a value of K, but we're going to look at this compensator here, and I'm going to create this one here. I'm going to call this the sys PI, which is basically going to be the transfer function of 1 and 0.1. Notice that the value of A that I'm adding in the model of the controller is a very small value. That way we don't have we're adding another 0, but it's a very small value that's very close to the origin. Any value that's close to the origin is really not going to have an effect on the overall system. And in the denominator, we have a 1 and 0. There might be an error here, and we're going to correct it in a moment. Oh no, it was okay. So now we have the controller. So first, let's trace the root locus of the system without the compensation, without the PI controller, and let's look at the root locus of the system that does have the control. Let's see how these look, how different they are. So the first root locus that I'm going to do is the root locus just of the system without with only the proportional controller. And then I'm going to do both of them. I'm going to do root locus of the combination of sys PI and sys plant. And I'm going to see those two graphs and see how they look. Oh, I didn't close the parenthesis there. There we go. And we should get the two graphs in a moment. So this is figure 2 and this is figure 1. These are the two root locuses. Notice that in the root locus on the left, this one here, we only have three poles, which are the original 3 poles that we had for the system. Okay, go back over here with the original 3 poles that we have. For the new root locus, we have still the 3 poles, 1, 2, 3, but we also have an additional one here at 0, which is the integral controller. And we have a 0 here also, which is the one we added. So it kind of reconfigures the root locus, okay? Let's assume that we're looking for a value of K let's assume that we're looking for a value of K for a certain overshoot. Let's assume that we're looking for a value of K for a, I don't know, 10 or 20% overshoot. Okay, so here we've got a 6.17. Let me do a zoom here. Whoops. I think I went too far. Let me first delete this one. And I'm going to do a zoom here on this section here. And let's look for a value here of K for this system, which is the one with just the proportional compensation. Let's look for a 10% overshoot. Let's see if I can reach that. Oh, this is terrible. I'm going to do a larger zoom there. I'm going to leave it at 10.1 just because my pulse isn't that good today. And then let's go over to this one and look at the values here. see if we can find also a value for, oops. $10.1. So for the first system, we've got a gain of 30.8, and the other one we've got a gain of 30.5. Okay, so let's test those out and see what type of responses we get, and let's see if we can get them, both of them, on the same. Let's see if we can get both of them on the same graph. So we're going to get, first I'm going to call it KP. I'm just going to call it, is going to be 30.8. And then I'm going to say that KPI is going to be, what did we say, 30.5. Okay, we've got those two values. Then I'm going to generate cis KP is going to be equal to the feedback of cis plant of KP times cis plant, comma 1. Okay, that's going to be the system, the first one. And then we're going to do cis KPI is going to be the feedback of KPI times the series of cis PI, cis plant, or actually I can put this KPI in here if I want, or I can leave it there, comma 1, and this is going to be the system, cis plant, there we go. And that's going to be the system with the controller. And let's, I think we can use, let's use the step of cis KP and cis KP. Give me a moment here. I don't remember if we can add more than one in the step. Maybe not. I don't remember if we can add more than one. We'll see. Okay, there we go. So notice, let's see which one is which. So notice something. I'm gonna erase this one. So the blue one is the response of the system without the compensation. So notice that the system has a stable behavior. It's got a jump, but notice that there's an error here. There's a large error because we've got a 0.6 here and we really want to reach the 1. Notice what happens when I add the proportional integral controller. Notice that the response now is a much better response that goes towards that is going towards the final value of 1 in a much more direct way. So again, the blue one is the system. The blue one is this first one that doesn't have a compensation, or the only compensation that it has is the K. And the red one is this one where we're adding the ideal, not ideal, we're adding the proportional integral action. And so notice again that in the case of the blue one, the system has an error, and it's this gap that we see here. In the case of the red one, which is the integral response, the error was reduced until it tends to be 0. Okay, and so what's the moral of this? By adding the proportional integral controller to the system, we automatically reduce we're automatically going to reduce the steady state error. Now, how we define the K and these values, we're gonna get to that when we talk about the PID tuning. Right now, we just did it with simple root locus design. We can do it that way. But there's some tips as to how to establish these values. The value of A that we're giving here is a 0. As long as it's a very small value that's very close to the origin, it's equivalent to just having the S over here on the bottom, which is what we're interested